First, I want to thank the HPC Advisory Council and Stanford for having me, allowing me to talk and give this tutorial. So this presentation really is set up as a tutorial. I wanted to talk about how to provision and manage InfiniBand clusters using the OpenFabric software stack. Just a little hint, a few of these things that I'm going to talk about are going to be probably part of this cluster challenge they talked about that we're going to have tomorrow. So either pay attention or I can slide you the slides, the deck after this so you'd have it for tomorrow. So let's talk first about the basics of the OFED InfiniBand stack. So OFED stands for OpenFabric's Enterprise Distribution. It's provided by the OpenFabric's organization. Basically, it's a software stack that's been built for RDMA-capable devices, including InfiniBand devices. The interesting thing about the stack is that it includes the low-level drivers as well as upper-layer protocols. So things like IP over IB and MPI, which I'll talk about, are included as part of the stack, as well as cluster tools and documentation. You can get the stack at openfabrics.org. Other vendors, such as including Mellanox, have their own version. Basically, what Mellanox takes the openfabrics.org release. We run some additional QA on it. We pre-build the RPMs for popular OSs, add some additional documentation, such as a user manual, and then distribute it through our website. So when you get OFED, the first thing you want to do is install it. I'm taking the Mellanox version as an example. It basically comes as an ISO. You mount the ISO and then you run a script called Mellanox OFED install. This will install the complete stack. You can also build RPMs for unsupported kernels. So I have a list here. I'm not going to go through this. Like many slides in this presentation, I sort of built it so you could use this as a representation to use to do things on your own. Okay, once you have OFED built on your system, there's various ways to control what modules get loaded and unloaded. For instance, there's a openib.conf file which controls boot time config.
Sorry, guys, it's really shaking, so I'm going to try to quickly fix it here for you. I'm sure your eyes are going nutty.
What's shaking?
Oh, the words.
Trying to drive it at 85 hertz or something?
It's a resolution thing?
Yeah, loose connection. Yeah, it looks like a loose connection kind of.
I know, I tried wiggling the cord.
Yeah, just see if you can go down to 60 hertz.
It's weird, I was just using this the other day.
Yeah, and how do you change the hertz here, Rich?
Oh, some advanced.
Sorry, we're HPC, we're not laptop oriented.
There's Steve.
Steve, do you know the password for this other one, by chance? Because this laptop's not working so well.
Just this.
Oh, it's right here. What the fuck's wrong with me?
My son.
Sorry.
That's what happens for not using a Mac.
Exactly. All right. Ladies and gentlemen, Todd Wilde.
Yay. Okay, so where was I? I was talking about OpenIB.conf. So this controls the boot time configuration as well as a bunch of other options. So you can, with OFED, there's lots of different modules it comes with. So you can actually control which modules get turned on or turned off through this OpenIB.conf file. You can see in this example, I'm saying, okay, load the driver on boot and also load IP over IB on boot.
How about IBSRP? Is that controlled through there?
The client is, yes. Yep.
You can put it in there.
Yep. I think what happens is when you build, if you build with all of the modules, it'll put those in there automatically. And I think it puts them in as yes, and then you can go in and change it to however you want. You can optionally manually start and stop services as well. There's a OpenIBD script in init.d, so it's pretty simple to do OpenIBD start or OpenIBD stop to turn on and off all of the InfiniBand services. So once I get my driver installed, how can I use InfiniBand? How can I send data? So one of the easiest ways is using something called IP over IB. What's IP over IB? It's basically an encapsulation of IP packets over InfiniBand. It uses InfiniBand as the layer 2, and then it uses IP for layer 3. It supports a couple different types of transport services, one called UD, one called RC. The only thing you really need to know about this is RC is better because it uses a mode called connected mode, which gives you much larger MTUs. So you can have up to 64 kilobyte MTU, which is the largest that Linux has. So you get much better performance using connected mode. It supports IPv4, IPv6. It does ARPs and DHCP just like you're used to with Ethernet. It has multicast support. It has VLAN support. And the real benefits of IP over IB is it's transparent for legacy applications. So anything that you can run over Ethernet, if you want to ping, if you want to SSH, do your normal socket data transfers, all of that just will work over InfiniBand seamlessly using IP over IB. So how do you configure IP over IB and get it working? Basically, IP over IB requires assigning an IP address and a subnet mask to each of the HCA ports. This is like any other, managing any other network device. If you do an ifconfig-a and you have IP over IB on, you're going to see an InfiniBand network interface for every single InfiniBand port you have in your box. So if you have 2 Ethernet ports and you have a dual port HCA, you're going to see ETH0, ETH1, IB0, IB1. And then you manage that IB0 network interface just like you would anything else. Any other network interface, you can assign it IP address statically using the network scripts methodology, using the ifconfig-IB0 file, which is I'm showing an example of here. Or you can use DHCP and just assign an IP address like you would any other network interface using DHCP. You bring the interface up and down by doing ifconfig-IB0 up or down. Okay, so pretty simple to get basic data transfers working on an InfiniBand network. Yeah.
Sorry to interject. I remember in the beginning, a couple of years ago, I had a really hard time getting NFS working over IP/IB. Has that been addressed anymore?
Yeah, I mean, people are very out of the box running NFS to NFS storage. No. And you're no problem interjecting. You can ask. It's better to ask questions as we go than wait till the end. Okay, that's IP over IB. Now let's talk about OpenSM. What's OpenSM and how to use it? So OpenSM is a subnet manager. A subnet manager is an entity in InfiniBand that sets up the IDs of the ports, sets up the links, and then sets up all the routing tables within the switches. Okay, so unlike Ethernet, which uses learning on its Ethernet switches to establish routes, InfiniBand has an entity in the subnet that's actually understanding the topology and setting up the routes for the switches. So the subnet manager is, there's a version of it called OpenSM. It's an InfiniBand compliant subnet manager, and it's included with the OFED stack. You can run several instances of OpenSM on the cluster and a master-slave configuration for redundancy. It has a bunch of other really nice features. One of those is QoS. So QoS allows me to have different service levels for different types of traffic. And then I can take those service levels and run them on what's called a virtual lane. And a virtual lane is really like a virtual fabric in my cluster. And I can have multiples of these virtual fabrics, up to 8 of them, that, in the fabric. So I can run storage and compute on completely separate virtual fabrics within my network. So that's what QoS gives me. It also gives me something called partitions, which are P keys that are very similar to VLANs. And then OpenSM has advanced routing algorithms. It has a basic routing algorithm called min-hop, but it has other ones like up-down and fat tree and door for different types of topologies. So these routing algorithms have different advantages depending on what your cluster looks like. I'm not going to go into all these, but if you look at the Mellanox OFED manual, it has full descriptions on all these routing algorithms. Yeah?
Is it a store and forward model, so the QoS stuff, a small packet on one of the fast lanes would get delivered even though a large packet is still in transit when it arrived and when it's delivered?
Yeah, so the way InfiniBand works, first the switches are cut through, they're not store and forward. Okay, so for very fast latency, we have cut through. Once you do have packets stored, though, they're basically input buffered and output queued. Once you have packets stored, each output port has its own arbiter, and those arbiters are controlled based on this quality of service. So the subnet manager knows what quality of service to give each service level, and it goes in and sets up these arbiters. So yeah, you can have traffic that's very low latency, that you want to be very low latency, and you can give it a higher priority, and then it will go out before the low priority traffic.
But if a long transfer is in progress and a short, higher priority transfer is initiated during that same time window?
Once the transfer starts with InfiniBand, you can't mix up packets. So
so there's not multi-GMA engines on the receiving controller that can handle things?
So there's messages. So you take a large message and split it up in packets, and you can split it up into small packets, small as 256 bytes. But once you start sending one of those packets, that packet's going to go out, and then another packet from another message can go out after that.
What about partitions?
So partitions is
Yeah, I know you're talking about partitions, but say I've got storage, and I've also got some other communication going on IP/OIP. So I've got an IBS/IP call, I've got an IP/OIP, and I use P key, and I partition them. Is it still okay? You get one packet, even though we're two subnets.
Yeah. So on the physical link, once you start sending a packet, that whole packet goes out, and then another packet's followed by that.
Okay, so the P key won't do like.
No, you don't have packets that are completely split up into a bunch of segments. So you just send the whole packet out. It has to be linear. But the good thing about InfiniBand is all of the transport offload in the Mellanox HCAs, all the transport offload is done in hardware. So you can do things like have big messages and split them up into very small, fine packets, and you don't get any performance hit by having these small packets, because it's the hardware that's putting all the packets back together into a message.
Real quick, in the IP/OIP implementation, is there any kind of latency hit? In other words, instead of running just IP verbs, if I'm running IP/OIP, am I going to take a...
Yeah, so with InfiniBand, you have a very low latency. It's less than 1 microsecond from memory to memory. And one of the reasons why it's that low latency is because user programs have direct I/O into the hardware, and they can completely bypass the kernel. So an MPI or something that's written directly over native InfiniBand verbs is really low latency. IP/IP is still using the TCP/IP stack inside the kernel. So you still have the inherent latency hits of that stack in IP over IP. So IP over IP is not your fastest or your lowest latency transport to use, or upper layer protocol to use to take advantage of low latency InfiniBand. So there's people writing networking stacks that sit in user space. They're lightweight networking stacks that directly access the hardware, and those you can achieve, you know, close to 1 microsecond latency, but you're not going to get that with IP over IP. Okay. So how do we run OpenSM? There's a few different ways to run it. One is from the command line. It's pretty simple. You just type OpenSM and hit enter. You can also give it a bunch of different flags. If you run OpenSM-H, you can see all the flags that you can use. For instance, I'm showing an example here where I change my routing engine to up-down by saying / routing engine up-down. The runs are logged to 2 different files. There's a varlog messages registers only major events, and then there's a detailed log file in OpenSM.log. You can also start OpenSM on boot or as a daemon. There's an OpenSMD startup file that you can use. Or you can go into your OpenSM.conf file and say on boot equals yes. Typically, you'll only run OpenSM on a couple machines in your network. You can simply run it on one machine and have that be the master, and it'll control your network. I can detect if it's running using OpenSMD status to see if it's running on my machine. There's also a utility called SMInfo. SMInfo shows all of the masters, or shows the one master and all of the standbys that are running in your cluster. And you can run SMInfo from any machine on the subnet and figure out where your subnet manager is running. So, for more details on the subnet manager, you can definitely check out. There's a full chapter in the user manual on OFED. Okay, so once I have IP over IP, I've got some basic data transfers running. I have my subnet manager configured and running. Now I can look at running some benchmarks and seeing what kind of performance I can really get out of my InfiniBand cluster. So first, let's look at some benchmarks that measure bandwidth and latency. These benchmarks come with the OpenFabric stack. And these benchmarks run directly over an interface we call InfiniBand Verbs. Okay, InfiniBand Verbs is a standard API that's defined by the InfiniBand spec that tells and specifies how a program can use the InfiniBand interface. So these benchmarks run in user space, directly talk to verbs, and they're going to give you some of your best performance indications on what InfiniBand can do. IB write bandwidth and write latency test the unidirectional or bidirectional bandwidth of the link, and then the latency tell how long it takes to get a packet from the sending side over to the receive side. Okay, the latency tests are memory to memory, so it's end to end. So how do you run these tests? It's pretty simple. You basically, these tests are run between 2 different machines. So you have one machine that you consider a server and one you consider a client. So on the server, you just give it the test name, and then you can give it any options you want. If you want to change the default message size, the default number of iterations, etc. On the client, you give it the same test name, and then you give it the server IP address of your server machine. This can be an Ethernet address, it can be an InfiniBand address, it really doesn't matter. You're just giving it that IP address to set up a control channel to set up your test. I can use -H to look at all the different options that these tests can give me. So here's an example. Lisbon 001 is my server. I'm going to do a IB send bandwidth test, so I just simply type in IB _send _bandwidth. And then on the other machine, Lisbon 2, I run IB _send _bandwidth, and then I give it the Lisbon 1 IP address. All right, here I'm just giving it Lisbon 1. I think the IP address is in my etc host file. So it sets up the test. It basically runs through a number of iterations, and then it gives me my results. It ran 1,000 iterations. Each message size was 64K. And then it gave me my average bandwidth and my peak bandwidth. So I'm getting around 2,700 megabytes a second on this particular machine. Okay, and that's a unidirectional. If I ran bidirectional, I would probably get about twice that. So this is it looks like a QDR machine, which is a 40 gigabit machine, and we're probably bound by the PCI Express bus, and we're getting about 2.7 gigabytes. Okay. There's other benchmarks I can run. I'm going to specifically talk about MPI benchmarks. So MPI, I think probably almost everyone here is familiar with what MPI is. It's a message passing library. We have various MPIs that run directly over InfiniBand. So the MPIs have been modified to run over the InfiniBand verbs. There's a OpenMPI, MVAPIC, MVAPIC2. Also, a lot of the commercial MPIs as well will run over InfiniBand. So if you want to get MPI running on your cluster, there's some prerequisites. This is actually talking about MVAPIC, and I'm using that as an example. Basically, there's a launcher called MPI run_RSH. This launcher requires automatic login to all the remote machines, so you need to get passwordless SSH access to the machines. You need to have an etc host file to specify the IP addresses of all the machines. And then basically you're ready to go. You're ready to launch MPI jobs on your cluster. So the basic format to do this is to use the MPI run launcher. You pass it the number of processes you want to run. So -NP8, for instance, would run a job with 8 ranks. And then you give it a node list, or you give it a file name that has the node list, and then you give it the program. Okay? Now the key is all of these machines you're going to launch on have to be able to see this binary program. So you either have to distribute it out, or it's got to be in some type of shared file system. There's a bunch of other flags that you can give with MPI. There's a bunch of parameters and environmental variables. For instance, this is one called viadev rendezvous threshold. The various MPIs that you use will have documentation on what those parameters are. So here's an example. I'm running a job on 2 cores, launching it on Lisbon 1 and Lisbon 2, and I'm running something called OSU latency. Okay, so you can see this OSU latency test kicks off, and I'm getting a latency of about, for small messages, about 1.36, 1.37 microseconds. Okay? And then once you get this running, there's all kinds of various benchmarks and things you can find to run on your cluster. Okay, so that's how to run benchmarks on your cluster. Now let's figure out how to diagnose your cluster. 1, diagnose it to make sure it's running at optimum performance, and then 2, diagnose things if you have problems. Now there's various commercial ways to do this and nice GUIs and everything, but everything I wanted to talk about today is in the OFED stack. Okay, so it's everything that's free diagnostic tools that you can deploy. So the first group of tools I'm going to talk about is called IBDiags. So this is the world of IBDiags. There's a bunch of tools that are single node tools, and when I mean single node, it's like you're going and identifying a node and trying to check some status of it. There's source destination pair tools, and then there's tools that look at things across the whole subnet. Now this is a ton of tools. I'm not going to go through all of these. I'm just going to really talk about 5 of them. And kind of highlight their usage. Okay, we're going to talk about IB status, SMP query, perf query, IB port state, and IBnet discover. I wanted you guys to have the list of tools so you know what's out there. I'm not going to go through all this, but it's just kind of shows you the depth of things that you can get. These are all the single node tools, as well as the source destination pair tools and the subnet tools. So before I go into how these tools work, I want to talk a little bit about the subnet management, and wow, that color really came across well. The subnet management and how things work in the cluster. Okay? Because how things are addressed and how the subnet manager manages things really helps you understand why the tools are doing what they're doing and what their output looks like. So here I have a cluster. It's a bunch of InfiniBand switches and a bunch of HCAs, which are endpoints in my server. Okay? And all of these little purple lines are just links that are connecting everything up. So first I have a subnet manager. We talked about this. The subnet manager typically runs on a computer or a server that's attached to the subnet. It can also run inside a switch. The subnet manager discovers this topology, initializes the routing tables, and does all the fabric management. And then every entity in my subnet, the HCAs and the switches, and any InfiniBand routers that may be there, must support a subnet manager agent. Okay, so they're all running a subnet management agent, and this agent is really there to just communicate with the subnet manager. So the subnet manager communicates with each, should be SMA, using subnet management packets. Sometimes you'll see them referred to as SMPs. I can also have a standby subnet manager supported. And I use local IDs to identify end ports or end nodes and to route packets. So basically what the subnet manager does is it goes through, it discovers my topology, and then it dynamically gives each of these ports a number. And that's called a lid. Okay? He starts typically out with number 1, and he goes 2, 3, 4, 5, and he gives everybody a number. So this port, if I want to talk to this port, I talk to lid number 8. All of the switches in my cluster know if it's lid 8 in the packet, they know to route it over to here. Okay, if I want to talk to this switch up here, I talk to switch lid 12. Okay, so this lid is an identifier to determine how to send packets and who to send them to. Okay, so all of the tools are using this lid number. And this lid number, by the way, is very dynamic. Okay, so depending on the cluster size, if you have 1,000 nodes, you'll have 1,000 lids, etc., and the subnet manager will dynamically assign these lids. Okay, so let's look at one of my tools. This is called IB status, and it gives me information about my device, about my HCA device. So if I run IB status in my machine, it'll give the output here that I'm showing. It displays basic information obtained from the InfiniBand driver. For instance, it'll include things like the GUIDs and the lids and the state of the ports. So here you can see my port state is active. That means I'm ready to transfer data. My physical link is up. And my lid is number 3. We talked about these lids. This lid of this particular port is lid 3. This lid is 1. Another thing you can see here is the subnet manager lid is 3 as well. So you can see I'm running the subnet manager actually on this machine. That's one way to tell. Okay, so this is IB status. So when you get to a machine, you want to see if it's up, if the port's ready to send, you can just type this and you're ready to go. It also tells me my rate. I happen to be running at 20 gigabits a second on this link, which is 4x DDR. IB port state, that allows me to look at the logical link and the physical link to see what speed I'm running at, and if the link's up. Now, this particular command I wanted to show you because it introduces the concept of being able to run these tools in band across the InfiniBand network. Okay, so I can run IB port state to any machine in my subnet. Okay, so here I give it a lid and a port. So I happen to be saying, okay, what's the IB port state of lid 56, port 3? Okay, so it happens to be a switch, and I can see my switch is running at a DDR rate, at 5 gigabits a second. So the concept is that with InfiniBand, you can do all of your management in band. You don't need a separate Ethernet network. All of these devices all talk in the same way. So every device will support this IB port state command. It's using basic subnet management packets that have been predefined by the spec. And it'll just work when you plug it in and talk to it. Here's an example of running perf query. Perf query queries my InfiniBand ports, performance, and error counters, and I can also use it to reset counters. So if I want to see how many bytes my port sent here, how many packets it sent, or how many errors it has, I can run perf query. And again, I can run perf query on any single port in my subnet. I just give it a lid and a port, and it'll query my port counters and return them back to me. So that's really one of the powerful things about InfiniBand. I have an InfiniBand attached laptop. I can plug it in my subnet and do diagnostics. The last node-based counter I wanted to show is SMP query. SMP query basically prints out all of the attributes of the port. So everything you want to know about this port and more, node info, port info, switch info, you can use SMP query. Okay, so I can use an SMP query, give it a lid of a switch, and ask it for the info of that switch, and it'll report how many ports the switch is and all kinds of characteristics about that switch. Okay, so that was the node-based tools. Now I want to talk about cluster-based tools that IBDiags comes with. The one I will tend to use the most is called IBNet Discover. And this will give you a cluster topology report. It'll show you exactly what your cluster looks like. It shows all of your lids. It shows your port GUIDs. A GUID is much like a MAC address. It's an identifier that never changes and is unique across all of InfiniBand cards. It gives me my host names, my link speed, etc. Okay. So here's an example of IBNet Discover. I'm giving it an option called a GUID map file. So you can have switches out there on your subnet that don't have host names. They're not managed. They don't have a CPU in them. So there's no host name at all. So the only way that the tools have to report what this switch is called is this really long GUID, which is this really long unique number. You can see an example of one of them right here. It's really, really long. So if I don't want to have to deal with all of these numbers all of the time, I can go read what the GUIDs are of all my switches, and then I can make this GUID to name file. So I can say this GUID is called switch number 1, this GUID is called switch number 2, and then it'll always use those names in my output. So here I'm running IBNet Discover. Basically, IBNet Discover shows me my topology in relationship to all of my switches and then all of my HCAs. So here, in this file, I have one switch right here. This is the name of this. It's called switch number 1. This is the type of switch it is. It's at lid number 9. So very important. If I want to query that switch, I need to know the lid. So this tells me lid number 9. And basically, I have 4 connections on this switch. I have port 5 is connected, port 6 is connected, port 14 and port 18 to different hosts right here. Okay, so I basically have a 4-node network. After all of if I had multiple switches, it would list every single switch. And then after all the switches, then it starts listing all the HCAs and it shows their connections. So conversely, I have this MTI Lab 47. His port 1 is connected to port 6. Here you can see it up here, 6, and MTI Lab 47. So it's the same connection. So it'll basically list connections twice, one in relation to the switch and the other in relation to the HCA. Okay, so this is how you see your topology. When you build your cluster, you run this command and you can see your topology, make sure everything's connected properly. Okay, so IBDiags is one set of tools. It's a bunch of tools, a bunch of pointed tools where I can get specific things from each of those tools. IBUtils sort of took all of those different IBDiag tools and rolled them into one nice package called IBDiagnet, which is a diagnostic tool for my whole network. When it's looking at topology, it can go out and it doesn't look at lids to do a topology comparison. Okay, it uses GUIDs and it uses host names. So. That? Okay. It'll also, IBDiagnet will give routing information. It gives histograms of hops between HCA to HCA, so it'll tell how many hops between, every single HCA in your cluster. So you can kind of see very quickly with this histogram if something's out of whack. It lists all the multicast groups and their members, and then it gives different errors based on all kinds of routing problems here, including credit loops and stuff that I'll go into. It does partition checks. It tells about if there's any mismatches in partitions, which I'll go into. It gives you IP over IB checks. And then there's been some new features that have been added to IBDiagnet recently. One is a bit error check. So it gives threshold and time between samples, so you can calculate your bit error rate across your whole cluster. It does QoS checks, so when you set up your QoS, IBDiagnet will make sure you did it properly. And it also gives cable reports. So it can give a complete dump of all of the cables that you have in your cluster. It can give you vendor information, part number, cable length, etc. of your cluster. Okay, so let's look at some examples of some failures that IBDiagnet can detect. First, we can report faults using topology comparison. Case number 1, I basically removed 2 cables between my cluster, and I run my IBDiagnet here, and the only flag I really give it is I tell it where my topology is, and it went through and it told me that I'm missing 2 cables in my cluster. I can remove hosts. And this is something a lot of the tools, they really don't do a good job detecting if there's not a host attached to your subnet because the host is down and they don't see any problem with the link. But IBDiagnet knows that all the hosts that should be there, and it'll tell you that you're missing 2 systems here that aren't part of your subnet. You can also remove a switch or a through within a switch system. So here I happen to just, especially like if you lose a spine sometimes in your system, you don't even know about it. The subnet manager routes around it. Everything's cool. It's just you're not getting full bisectional bandwidth because there's some spine in your upper layer of your cluster that went out. So here I can do a topology match and I can say that there's a particular system board that's not in my cluster.
So case 2, you've got to have the driver or the daemon running on the host that supports the HCA?
No.
So you just have to have power to the HCA?
You don't even have to have power. Here it's detecting that there is no link. So it's saying that this system should be connected to this switch, but it's not there. So the host is basically turned off.
What's the difference between that and thinking that the cable's not there?
I see what you're saying. That's a very good question. Oh, you know what? I don't think it knows. It doesn't know if it's a cable or a host that's down. That's why the report it says should be connected by cable. So it's saying it's missing a system. I think this one is missing. This one detects cables between 2 switches. So here it's cable between 2 switches, and here it's a cable between a switch port and an HCA. So it's almost the same thing, but the output's a little different on how it detects it, on what it's reporting. Because you can see here switch to switch, and here it's missing. It should be connected by cable. So this could be a cable down between a switch and an HCA, or it could be the host is completely off. You don't know. You do know that when a lot of the cables now, they come with identifiers. So when the cable is plugged in, you can get a report of the cable. So you could actually tell that if the cable's in versus if the host's down. I don't know if this tool is sophisticated enough to do that.
Because they look like G-bits.
Yeah. That's how IBDiagnet gets the cable reports. There's a little E² prom inside the cable that has part number and when it's been built and everything.
Does that only on the QSFP cables or is that 646?
Just on the QSFP. Yeah, there's a little management bus on the QSF piece. Okay. So here's a little helpful hint. I talked about this. You can write out the topology. So you can build your own topology by text. Sometimes you'll do that before your cluster even arrives because you're so excited and you want to really be able to run these tools quick when you get it. But if you want, you can also wait till your cluster's built and you're sure that you've gone through IBNet Discover one time and make sure everything's in place, and then you can write your topology out. And then you can kind of have that file as your golden file and use it to do periodic maintenance checks as you go along. Okay, so here, I show you how to do that here in this slide. Okay, let's look at cable connector faults and link faults. So link faults are bad cables. You can have cables that aren't plugged in all the way, so you're sending data, but you may not have the right speed, you may not have the right width. You may have a marginal cable where you're throwing bit errors that are excessive. So IBDiagnet finds this with error counters, which will report any bad issues. IBDiagnet will report link faults across the network. So when any port counter changes rate larger than a threshold that you've defined in a configuration file for IBDiagnet, you'll get this report. Okay, so here I'm reporting a bunch of different counters, and basically I've exceeded my threshold. These show up as port receive errors. So they're basically CRC errors that have shown up on packets on these ports. So when you build a cluster, it's really important to do this to check out that you don't have any bad cables. Things will seem like they're running fine, but you're not running at optimum performance. So what you'll want to do is use IBDiagnet, look at all the error counters, and then really stress your cluster out. Run MPI across your whole cluster on every single node, something like IMB that really stresses the I/O. Run that for a few hours, and then run IBDiagnet again and see if you have any bad cables. It's a really good practice to get into. Here I'm using IBDiagpath. I'm showing you the output looks almost the same. The command line looks almost the same as well, but I'm running it from a point to point. So I'm running it between myself and host H-3. So sometimes MPI jobs, you'll get really a lot of errors on a link, and your MPI job will fail. So if your MPI job fails, it usually gives you the host there was some timeout on a data transfer. So you can actually run IBDiagpath between those two hosts, and you'll identify right away if there's some physical issue that caused the problem. Okay, so IBDiagpath is more of I want to pinpoint. I've got one bad host or a couple bad hosts, and I need to pinpoint what the problem is. Okay, that's the basic set of tools that you can do with IBDiagnet. I want to go into a few kind of advanced utilities or advanced checks that IBDiagnet does, just so you know. You won't be tested on these later, but they are good to know. So first is Subnet Manager faults. So I already talked about the Subnet Manager quite a bit. It's mandatory for setting up port IDs, links, and routes. So IBDiagnet will do a bunch of Subnet Management reporting. It'll make sure that there's one and only one master on your subnet. It'll make sure that the neighbor MTUs are correctly set up. And it'll make sure you have unique lids assigned across your whole cluster. So here I ran it. I have probably the number one error you see is no SM. So it reports missing master SM in the Discover fabric. An interesting thing about IBDiagnet is a lot of its functionality uses something called direct routes. So when the Subnet Manager sets up the route tables, everything's routed based on a lid, right? We talked about these lids. There's something called direct routes, and a direct route is I don't give the lid and let the switch figure out how to route it. I figure out exactly how I want the packet to get somewhere, and I give it a direct hop-by-hop indication in the packet. Go to port 6, go to port 5, go to port 2. That's a direct route. The switch doesn't even need to be configured for those to work. So IBDiagnet actually uses those. So you can have, your fabric can be in really bad shape, no SM running and nothing configured right, and you can still go diagnose your links and see if things are working because IB Diagnet will use these direct routes. So here's a case where my IB Diagnet run went fine, but I didn't even have a subnet manager on my fabric.
Go back. How do you get two master subnet?
Let's see. It's really hard to happen. In fact, I think I was trying to do a case to create it. I noticed this the other day and I didn't fix it. I said hard to create because I couldn't.
Yeah, I've never.
It was usually. It could be either. It could be some race condition or some problem with your SM, some bug with a race condition where there's two masters, but I've never seen it. And then here's some fabric quality reports. It failed to find a path between two hosts. A lot of times when you get this, it's usually some routing problem or some cabling problem where you've got something not cabled right up properly, and the SM can't even figure out your topology. So you've got some bad cabling issue. So another thing that can happen to networks, and IB Diagnet is great at finding this because it's one of the few tools that actually can find it, is something called a credit loop. So what's a credit loop? So whenever I have a lossless fabric, I use something called link level flow control to make sure that my packets don't get dropped if there's no room in a buffer to store them. So link level flow control basically says my buffer's full, don't send anything else. So it tells my sender, don't send to the receiver, there's no buffers to put the packet in. So when you have a credit loop, when you have link level flow control, something called a credit loop can be a very bad thing. And why is this? Here's a loop. This is a loop. Red packet wants to go out here, green packet wants to go out here, and black packet wants to go out here. And these little boxes are buffers in my switch. So everybody sends at the same time. Now, my buffers are full, so everyone has to stop. And you'll notice that there's a predependency for everyone on everyone else. So black can't go because red can't go, and red can't go because green can't go, and green can't go because black can't go, because we looped. Okay, this is called a credit loop. If this happens in your cluster, you'll see things running from really, really, really nicely to slam down to nothing. Okay, so credit loops are bad things. And then they'll clear themselves up, and then everything will be fine again. You'll say, what just happened? And it'll be this. So how can credit loops happen in the real world? So here's a fat tree cluster. All these are my hosts. Basically, to get from here over to here, I have to go all the way up and then all the way down. And this is a pretty simple example, pretty straightforward how we build InfiniBand clusters. And we use algorithms called up-down, where we go to the top of the tree and then we go back down to the bottom. So here's an example of things run fine. Now, with this type of architecture, whenever you have traffic, you notice how I always am going up and then I'm always going down? If you ever have traffic that goes down and then back up, if there's ever any traffic patterns like that, that's when you have credit loops. Okay, you never want to go down and then back up. Okay, you can see I'm not doing that here. But I can do that if I have some type of wiring or miswiring in my cluster. So here, this guy really wanted to go over to this one, and then this one wanted to go over to here, etc. But this guy was miswired and he went over to this leaf. So now I can get there in a different way than I should be able to. Okay, I can go from here to here by, instead of going up to here, I can actually go down to here and back up because of this miswiring. Okay, so this simple flip of the cables caused a credit loop. Okay, everything will run fine. You won't see this problem until maybe you'll never hit it. You have to have a magic traffic combination to hit it. So you may never hit this problem at all, but the potential's there. So IB Diagnet finds this problem. Basically, it checks for credit loop. It analyzes the whole fabric for credit loops. And if it finds any particular credit loops on a switch in a port, it'll indicate it. Okay? And then you need to go try to figure out your topology and figure out why you happen to have that type of credit loop. I think it's one of the few tools I've seen that'll do this, so very valuable. Partitions, we talked about partitions a little bit. They're similar to VLAN IDs, but they're enforced on the switches and the host ports, unlike VLANs. VLANs are typically done on the switches. So partition enforcement by leaf, you could have a leaf switch mismatch or a leaf host mismatch for partitions because you set something up wrong. That's typically the error I've seen. All these partitions are configured through a partitions.conf file, and then the subnet manager sets them up. But you could have a problem, and then if you have this problem, you won't be able to communicate on that partition, and you won't know why. So here's an example where I have 3 different partitions. I have partition 1 and partition 2 in my fabric. And I have a host and a switch where this host supports partition 1. 8 is a special bit. He supports partition 1, but I didn't set my switch to support partition 1. Okay, so the host will send things out on that partition and everything will work fine. The switch will say, hey, I don't support this P key, and it'll just drop the packet. So IBDiagnet will come to my rescue again, and it'll go through and check every single link, and it'll look at the pair, and it'll make sure they both support the same P key. So it'll report an error on this problem. And then the last error I wanted to talk about was IP over IB errors. Each IP over IB has a subnet that's attached to a partition and a broadcast group. And that broadcast group has a particular rate. So the broadcast group may be 40 gig, and you have, or maybe 20 gig, and you have members that can support 40 gig that are trying to get access to that broadcast group. So you really want the same speeds to be part of the broadcast group. So here I'm giving a warning saying the device cannot join because its rate is less than the rate of the broadcast group. And then here I'm saying there's a suboptimal rate of, these guys have more bandwidth capabilities than the group that they're joining. Okay, so just different errors of warnings for IP over IB. Okay, that's all I had. I think it's a great tool. It's available in OFED. There's complete documentation in the Mellanox OFED user manual. Any questions?